In this video we look at the work on roots of polynomials for the first unit of the Further Maths qualification. The specification requires us to be able to solve quadratic equations with real coefficients, to solve cubics and quartic equations with real coefficients, given sufficient information to make initial progress. We're required to know that non-real roots of polynomial equations with real coefficients will occur in conjugate pairs. We need to understand and use the relationship between roots and coefficients of polynomial equations, including quadratic equations, cubic equations and quartic equations. And we ought to be able to use simple transformations to obtain a new polynomial equation whose roots are a linear transformation of the roots of a given polynomial equation. In terms of key facts, we certainly will need to know that if we have a polynomial whose coefficients are real and that u plus iv is a root of f, then u minus iv, the complex conjugate of the original root, must also be a root of f. For quadratic equations, we ought to know that if ax squared plus bx plus c equals 0 has roots alpha and beta, then alpha plus beta is minus b over a, and alpha times beta is c upon a. If we have a cubic equation, ax cubed plus bx squared plus cx plus d equals 0 with roots alpha, beta and gamma, then alpha plus beta plus gamma is minus b over a, alpha beta plus beta gamma plus gamma alpha is c upon a, and alpha beta gamma is minus d over a. And for the quartic equation, ax to the 4 plus bx cubed plus cx squared plus dx plus e equals 0. If that has roots alpha, beta, gamma and delta, then alpha plus beta plus gamma plus delta must be minus b over a, alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta must be c upon a. Alpha beta gamma plus alpha beta delta plus alpha gamma delta plus beta gamma delta must be minus d over a. And alpha beta gamma delta must be e upon a. There are one or two useful algebraic results that we might need in these questions. First of all, alpha squared plus beta squared is the same thing as alpha plus beta all squared. Take away 2 alpha beta. Alpha cubed plus beta cubed is the same thing as alpha plus beta all cubed minus 3 alpha beta times alpha plus beta. And alpha squared plus beta squared plus gamma squared is the same thing as alpha plus beta plus gamma all squared. Take away 2 lots of alpha beta plus beta gamma plus gamma alpha. So, our first example, we're told that the equation x cubed plus 2x squared minus x plus 28 equals 0 has got an integer root. Using that fact, we've got to determine the exact values of the 3 roots of the equation. Well, let's start by having a think about the integer root. Let's suppose it's n. Well, if n is the integer root of the equation, we know that n cubed plus 2n squared minus n plus 28 must equal 0. In other words, we know that 28 is n minus 2n squared minus n cubed, which means that 28 must be n times 1 minus 2n minus n squared. N is a whole number, 1 minus 2n minus n squared is a whole number. So we've got n is a factor of 28, which means that we certainly know that n is plus or minus 1, or plus or minus 2, or plus or minus 4, or plus or minus 7, or plus or minus 14, or plus or minus 28. So we've got two things. We know that f of n has got to equal 0, where f of x is x cubed plus 2x squared minus x plus 28. And we also know that n must be plus or minus 1, or plus or minus 2, or plus or minus 4, or plus or minus 7, or plus or minus 14, or plus or minus 28. Now, using our calculator, we can very rapidly work out the different possible values of f of n for these values of n. So f of 1 is 30, that's no use to us. F of minus 1 is also 30, again, that's no use to us. F of 2 is 42. That's no use because we're looking for f of n equals 0. F of minus 2 is 30. Again, that's no use. F of 4 is 120. No use again. However, f of minus 4 is 0. Okay, now we can check that that calculation is right. Minus 4 cubed is minus 64. 2 lots of minus 4 squared is 32. And I've got minus minus 4, so that's a plus 4, and I've got the 28. So f of minus 4 is going to be minus 64 plus 32 plus 4 plus 28. And that is indeed 0. So I know that my integer root of the equation is minus 4. So minus 4 is the integer root of f of x, so I certainly know that x plus 4 must be a factor of f. So we can say that x cubed plus 2x squared minus x plus 28 is the same thing as x plus 4 times by, well, certainly I know I'm going to have an x squared at the beginning of the second bracket. And that's to make sure I get the x cubed when I multiply out. And I also know I'm going to have plus 7 at the end of the bracket, because I know that at the end of the multiplication out, I'm going to have 28, and the only place I'm going to have a constant term coming from is the 4 times the number at the end of the second bracket. So the number at the end of the second bracket has to be equal to 7. There's almost certainly something in the middle of that second bracket, an x term. We're going to need to try and work out what that's going to have to be. Okay, so let's have a think. On the left hand side we've got 2x squared. On the right hand side, the x squared terms are going to come from x times by ax, which will give me ax squared, together with 4 times x squared, which gives me 4x squared. So for this expansion to work, I certainly need to have 2 to be the same as 4 plus a. In other words, I need a to be negative 2. So we have the factorisation x cubed plus 2x squared minus x plus 28 equals x plus 4 times by x squared minus 2x plus 7. One could even check at this stage that the x terms also work. Where will the x terms come from when we multiply out the right hand side? Well, the x terms will come from the x times 7, which gives me plus 7x, together with the 4 times minus 2x, which gives me minus 8x. So I've got 7x together with minus 8x, which gives me minus x, which is exactly what I want when I look at the left hand side. So I've got my factorisation now. So solving the equation x cubed plus 2x squared minus x plus 28 equals 0 is equivalent to solving the equation x plus 4 times x squared minus 2x plus 7 equals 0. So we've either got x plus 4 equals 0, or we've got x squared minus 2x plus 7 equals 0. X plus 4 equals 0 gives me x equals minus 4. X squared minus 2x plus 7 equals 0 is a simple quadratic equation. We could solve it by completing the square, by using the formula, or indeed if you've got access to a calculator which solves quadratic equations for you exactly, then you could use that calculator for getting your solutions. So we're ending up with x is minus 4 or x is plus or minus root 6 times I. Move on now to a second example. We have to consider the polynomial equation x to the 4 minus 2x cubed minus 2x squared plus 6x plus 5 equals 0. And we're told that one of the roots of this equation is 2 plus I, and we've got to determine all of the other roots of the equation. Well, we have a polynomial equation with real coefficients. So that means that the complex solutions must appear in pairs. If we have a complex root, then the complex conjugate must also be a root. So we must have 2 minus I as one of the roots as well. The fact that 2 plus I is a root tells me that x minus 2 plus I must be a factor. The fact that 2 minus I is a root tells me that x minus 2 minus I must also be a factor. Putting those two factors together, we've got that x minus 2 minus I times by x minus 2 plus I must be a factor of the polynomial. Notice both of those brackets have got x minus 2 in common. And what we've really got now is something of the form p minus a, where p is x minus 2 and a is I, times by p plus a. So we've got p minus a times p plus a, which is just p squared minus a squared. So I know that those two factors that I've got of the polynomial multiply out to give me x minus 2 squared, take away I squared. In other words, x squared minus 4x plus 4 minus 1, which is x squared minus 4x plus 5. So the fact that 2 plus I is a root tells me that 2 minus I is a root. And we've now been able to deduce from those two facts the fact that x squared minus 4x plus 5 must be a factor of the polynomial. So we can now try and do a little bit of factorisation. We've got x to the 4 minus 2x cubed minus 2x squared plus 6x plus 5 has got a factor of x squared minus 4x plus 5. What goes into the second bracket? Well, first of all, we've got to make sure we can get the x to the 4 out when we multiply. So we're going to need an x squared in the second bracket. At the far end of the second bracket, we're going to need a number. 5 from the first bracket times the number that we put in the end of the second bracket must multiply together to give me 5 on the left hand side. So what I must have there is simply a plus 1. So at this stage here, I've got the x to the 4 sorted out at the extreme left of the left hand side. I've also got the 5 at the extreme right of the left hand side sorted out. there's almost certainly going to be something going into the middle of the second bracket. Okay, and what we'll do now is we'll concentrate on the x cubed terms. Now, on the original polynomial, we have minus 2x cubed. If we multiply out our brackets, the x cubed terms are going to come from x squared times by ax, together with minus 4 times by x squared. So I want minus 2 to equal a minus 4, which means that a must be 2. So I've now got my factorisation. X to the 4 minus 2x cubed minus 2x squared plus 6x plus 5 is x squared minus 4x plus 5 times by x squared plus 2x plus 1. In other words, I've got x squared minus 4x plus 5 times x plus 1 squared. So, we know that the roots of x squared minus 4x plus 5 equals 0 are 2 plus I and 2 minus I. We know that the roots of x plus 1 squared equals 0 is simply x equals minus 1. It's a repeated root. So the roots of x to the 4 minus 2x cubed minus 2x squared plus 6x plus 5 equals 0 are going to be 2 plus I, 2 minus I, and minus 1. And the minus 1 is repeated. We've got it occurring twice. Moving on to our next example. We've got the cubic equation x cubed minus 3x squared plus 2x plus 4 equals 0, has roots alpha, beta and gamma, and we have to prove that beta gamma over alpha plus gamma alpha over beta plus alpha beta over gamma equals minus 7. Now on examples like this, it is a very good idea to start by writing down what we know about the values of alpha, beta and gamma. It's a cubic equation. So we know that alpha plus beta plus gamma will be minus b over a. B is the x squared coefficient, which is minus 3. A is the x cubed coefficient, which is 1. So minus b over a is minus 3 over 1, which just gives me 3. We know that alpha beta plus gamma alpha is c upon a, where c is the coefficient of x and a is the coefficient of x cubed. So in this case we have got alpha beta plus gamma alpha is 2 over 1, which is 2. And finally we've got alpha beta gamma is minus d upon a, where d is the constant coefficient at the end of the cubic equation and a again is the coefficient of the x cubed. So in this case we've got alpha beta gamma must equal minus 4 over 1, which is negative 4. Okay, so we've got those results sorted out. Now what are we doing? We're looking at beta gamma over alpha plus gamma alpha over beta plus alpha beta over gamma. We're adding 3 fractions. If we're adding 3 fractions, the sensible way of progressing is to move to having a common denominator and then work with the common denominator. So, common denominator for alpha, beta and gamma is going to have to be alpha, beta, gamma. Now with the first fraction was beta gamma over alpha. We have multiplied the alpha by beta gamma to move to the common denominator. We need to do the same to the top. So we're going to end up with beta squared gamma squared over alpha beta gamma for the first fraction. For the second fraction, we started with a denominator of beta. To move to the common denominator, we've had to multiply by alpha gamma. We need to do the same to the top. So the top now is going to be gamma squared alpha squared. And for the third of the three fractions, we started off with the denominator of gamma. We have to multiply that by alpha beta to move to the common denominator. We have to do the same to the top. So we have got alpha squared beta squared on the top. Now, alpha beta gamma we know is minus 4. At the moment though, we don't know the value of beta squared gamma squared plus gamma squared alpha squared plus alpha squared beta squared. So we're going to have to think about that. Now what have we got? We've got something that is simply the sum of three squares. So we've got beta gamma all squared plus gamma alpha all squared plus alpha beta all squared. And if we remember that p squared plus q squared plus r squared is the same thing as p plus q plus r all squared, take away two lots of pq plus qr plus rp, we see that we can write beta squared plus gamma squared plus beta squared gamma squared plus gamma squared alpha squared plus alpha squared beta squared is the same thing as beta gamma plus gamma alpha plus alpha beta all squared. Take away two lots of beta gamma times gamma alpha times alpha beta, and alpha beta times beta gamma. So that's beta gamma plus gamma alpha plus alpha beta all squared. And the second term has got a common factor of 2 alpha beta gamma running through it. So the second term can be tidied up as 2 alpha beta gamma times by alpha plus beta plus gamma. We know that alpha beta plus beta gamma plus gamma alpha is equal to 2. So the first bit that we've got there is simply 2 squared. The second bit that we've got is 2 times by alpha beta gamma, that's negative 4, times by alpha plus beta plus gamma, which is 3. So I've got 2 squared is 4, take away minus 24 gives me 28. So beta squared gamma squared plus gamma squared alpha squared beta squared is the same thing as 28. So I've got 28 divided by minus 4 equals minus 7 for the value of beta gamma over alpha plus gamma alpha over beta plus alpha beta over gamma. Okay, our final example then. We have the equation x to the 4 minus 3x cubed plus 12x squared plus 126x minus 136 equals 0 has got roots of alpha, beta, gamma and delta. First thing we have to do is prove that alpha squared plus beta squared plus gamma squared plus delta squared is equal to minus 15, and then deduce how many real roots this equation has. Okay, we know that alpha plus beta plus gamma plus delta must be equal to minus b over a, which is going to just give me 3. We also know that alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta must equal c upon a, which is 12 over 1, which is 12. Now, alpha squared plus beta squared plus gamma squared plus delta squared is the same thing as alpha plus beta plus gamma plus delta all squared. Take away 2 lots of alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta. So it's the same thing as 3 squared take away 2 times 12. And 3 squared take away 2 times 12 is minus 15. So we've now got to deduce how many real roots this equation is going to have. Well, if we let y equal x to the 4 minus 3x squared plus 12x squared plus 126x minus 136, first very obvious thing is that when x is 0, y is minus 136. What's more, because it's an x to the 4 graph, we certainly know that if x tends to infinity, y is certainly going to tend to infinity. But if x tends to minus infinity, y is also going to tend to plus infinity. So those simple observations means that I've got that much information about the graph. I know the graph is continuous, so there aren't going to be any sudden jumps in the graph of y equals x to the 4 minus 3x squared minus 3x cubed plus 12x squared plus 126x minus 136. So, because it's a continuous graph, there must be at least 2 real roots. Okay. From part 1, though, we know that if we add up the squares of all of the roots, we end up with minus 15. If we had 4 real roots, then if we added up the sum of the squares, we would get a number that was at least 0. So part 1 tells me I must have at least 1 complex root. But if an equation with real coefficients, I have an equation with real coefficients, then we know that the complex roots appear in complex conjugate pairs. So if I have 1 complex root, there must be another complex root. So I now know that I've got at least 2 real roots and at least 2 complex roots. But I've only got a polynomial of degree 4, so there are only going to be 4 roots. So we must now conclude that we have 2 real roots and 2 complex roots. Let's move on to part B of this question then. We've got to find a quartic equation whose roots are 2 alpha plus 3, 2 beta plus 3, 2 gamma plus 3, and 2 delta plus 3. Now, we know that the equation x to the 4 minus 3x cubed plus 12x squared plus 126x minus 136 equals 0 has got roots alpha, beta, gamma, and delta. And the key thing to get this started off is at this stage to say, right, let's have y equals 2x plus 3. In other words, x is y minus 3 divided by 2. So, if I replace every occurrence of x in what we just had by y minus 3 over 2, I can say that the equation y minus 3 over 2 to the power 4 minus 3 lots of y minus 3 divided by 2 to the power 3 plus 12 lots of y minus 3 divided by 2 to the power 2 plus 126 lots of y minus 3 divided by 2 minus 136 equals 0 has got roots of y minus 3 over 2 equals alpha, beta, gamma, and delta. Now what we really need to do now is tidy up that rather messy statement. First stage of tidying it up is to deal with the fractions. So I've got y minus 3 to the power 4 divided by 16 minus 3 lots of y minus 3 cubed over 8 plus 12 lots of y minus 3 squared over 4 plus 126 lots of y minus 3 over 2 minus 136 equals 0 has roots of y equals 2 alpha plus 3 or 2 beta plus 3 or 2 gamma plus 3 or 2 delta plus 3. Okay, so that's exactly what we had at the bottom of the previous page. We're going to multiply up by 16, first of all, to clear the fractions. If I multiply up by 16, I've got y minus 3 to the power 4 minus 6 lots of y minus 3 cubed plus 48 lots of y minus 3 squared plus 1008 lots of y minus 3 minus 2176 equals 0. And at this point, what I need to do is I need to make use of Pascal's triangle to expand y minus 3 to the power 4, y minus 3 to the power 3, and y minus 3 squared. So the y minus 3 to the power 4 expands out as y to the 4 minus 12y cubed plus 54y squared minus 108y plus 81. Y minus 3 cubed expands out to y cubed minus 9y squared plus 27y minus 27. And y minus 3 squared expands out as y squared minus 6y plus 9. And that stage there, I can now just tidy everything up, collect together all of the y cubed terms, collect together the y squared terms, collect together the y terms, collect together the constant terms, to arrive at y to the 4 minus 18y cubed plus 156y squared plus 450y minus 4525 equals 0 has got roots of y equals 2 alpha plus 3, 2 beta plus 3, 2 gamma plus 3, or 2 delta plus 3.